Okay, everyone. So this is going to be the lecture 7 of this ISSS course on applied differential geometry in mechanics. So as we had learned in the previous session, so we went on to understand how do we form the so to speak the assumptions of made in RUDs to study RUDs, and before that we began with how do we define a rod in terms of it's an extension to beam structures. And then we proceeded to give some basic assumptions made with respect to the cross sections, the orientations, right? And then we talked about the kinematics of rods and how it's a map, how the deformed configuration is a mapping from the reference configurations. Specifically here for the case of a straight rod. In general, of course, you can have a pre-curved rod as well, right? So then we moved on to talking about the mathematical aspects of how do we present the deformation. Right? Then we made some assumptions for the particularly the quadrat rod that we have been studying here in terms of how the directed bases are oriented relative to each other. And in this quadrat rod, we assume that we have this condition that D1 and D2 may not be orthogonal, which implies that which allows for the possibility of shear deformation of the cross section or shear deformation of the rod's cross section, essentially. Right? And both these vectors are unit normed. Then using this, we could construct the third basis vector, which is D3. And D1, D2, D3 happens to form a triad of basis vectors. And D3 is perpendicular, of course, to both D1 and D2 by virtue of its being or the vector, so to speak, the vector calculus, right? Then we call that a quadrat rod happens to be a nonlinear version of the Timoshenko beam. And the further assumptions we made to simplify this quadrat rod is for practical purposes is for this what we call as the Kirchhoff rod. And Kirchhoff rod, we assume that this triad D1, D2, D3 happen to be orthogonal and are unit normed, thereby orthonormal, right? And in this case, we do not allow for any shearing. We do not allow for any shearing of the rod, and the cross sections remain perpendicular to the center line after deformation. Now we wanted to understand what is this the rotation matrix, which is also a function of the arc length coordinate s, right? So it happens to map the standard Cartesian basis to D1, D2, D3 through this relation di is equal to r of ei. And then we have this deformation mapping, which is x vector capital X1, X2, and Xs, which are the so to speak the material coordinates, where X1 and X2 determine the or are used to represent the coordinates of the cross section, and S is the arc length coordinate along the center line. And then we could then we have this rotation matrix, which can be formed by simply um, stacking side by side the basis vectors D1, D2, D3. It also showed that just to verify whether this mapping is really true, we just showed through a simple just for the case for E1. We make further assumptions that the center line is inextensible. Thereby, what we have is that r prime of s, the norm of that is 1, and so d3 is equal to r prime s. Now for the static equilibrium equations. So we have a segment of this, segment of the center line from s to s plus ds. We isolate that part, we constructed one body, so to speak, a free body diagram of that. Then we could derive this conditions, I mean, two equations for balance of forces and one for the balance of moments, right? In terms of vectorial representation. Now, what we would like to do is, so we have this. So today we'll talk about energy functional and then move into a bit of ribbon theories. Right? So let me just pull up with these equations. Them here. Now, mind you that both these equations are in vectorial form, right? They're all vectorial equations. Rather, vector equations. Right? So, however, we would require it to represent, for the purpose of computation, we need to present it in some uh, so we need to, so these are the equations in vector form. That's it. And the best way would to be to call them as, so like balance equations in vector form. Now we would want to add them, we rewrite them in component form. Before we would do that, we would want to recall some of the things that we had learned in the lectures on the space curves. So we had determined that the evolution of director basis is d1 of s, d2 of s, and then d3 of s. The way they take place is so the way they evolve is, so di prime of s is equal to kappa vector of s cross what I is equal to 1, 2, and 3. Right? So where the rotation matrix or the Darboux vector, rotation gradient or the Darboux vector, It's also sometimes called as a strain gradient or rotation gradient. This kappa, that is represented in kappa 1, because all of them are functions of S. This kappa 2, S D2S, either kappa 3 of S, D3S, or sometimes we also call this kappa 3 of S as tau of S, right? So it means the same thing. Now let's try to let's develop these equations for all of them, or maybe even before expanding it. Now what we can do is, so let's pick up the first equation. So we have n prime cross p vector of S is equal to 0 vector, right? So n prime, mind you that here we are representing a differentiation with respect to S. And you know that S is an arc length coordinate. So what will happen is, even the differentiation, say before that, say we represent, so let's say we represent n vector of S, p vector of S, m vector of S, and say what is the fourth quantity was q of S as something like ns vector is equal to ni of S di of S, where it implies summation, right? It implies summation over I. This is the same as I is equal to 1, 2, 3 ni of S di of S. And n vector of S is like mi. Right? So with this, what happens is, and now we can write this equation as ni of S di of S prime plus pi of S, right? And here we use this chain rule. So it will be ni prime of S. So it should no longer be vectorial. Ni are components, right? So it will be n I prime of S dis plus ni S prime of S plus equal to 0 of S, right? And then this we can write it as ni prime of S di of S plus ni of S, and this would be a kappa vector cross di, right? Pi of S, isn't it? So what we can do here is that we can form this in terms of So here we have to do is we have to expand this. So you recall very well that this can be written as epsilon I j k kappa j and of S and D it will be D K of S. Say for I is equal to 1, it can be written as epsilon 1 jk kappa js dks. So this will be equal to so this one will be written as so epsilon 1 to 1 to 3, right? So epsilon 1 to 3 kappa j, sorry, kappa 2 d 3, then plus the other surviving quantity is going to be 132. So it will be kappa 2 kappa 3 d2. So thereby we can write it as kappa 2 d3 minus kappa 3 d2. Right? That is the property of this permutation symbol. Let's just verify. So you have kappa 1 d1, kappa 2 d2, kappa 3 d3 cross d1. It will be d1 is 0, d2. So d2 cross d1 is minus kappa 2 d3. Okay. So kappa 2 d2 cross okay, I think so. We made some mistake in terms of so this will be kappa 2, kappa 3, d3 cross d1 is d2. This is kappa 3. Okay, so this would have been written so maybe something along these lines. If you can call it minus. So a better way would be, I think we can put it that way. Yeah. Minus, so we have so this will be minus. So now it's consistent, right? Fine. Okay, so this we can now see that we can write this in terms of so we have to write in components I is equal to 1, or maybe if for a general framework, say take dot product with d1 or di vector, then what we have is ni prime of s di of s plus s kappa of s cross di of s dot di So maybe plus throughout, say, this whole dot di into 0. So this will give us ni prime of s plus nis and then kappa of s cross di. Px. So this will be component wise. Right? So this is for I is equal to 1, 2, 3. And likewise, a similar case uh, for moments as well. You will have a similar sort of equation, except that what we have known is that m prime of s plus r prime cross n3 n of s plus q vector of s is equal to 0. And this we recall that it is d3 because of the inextensibility condition for Kirchhoff rod. And this implies that what we do is we have, again, a similar fashion. We have mi di of s whole prime plus d3 cross n vector of s plus qi. This will be ni s di of s plus qi of s di of s. And in a similar format, we can just have something represent the components for M1, M2, M3. That can be easily shown, right? So maybe it will be Mi prime of S d1 plus Mi of S kappa vector of S cross di of S dot di. Then we have plus this whole quantity d3 cross ni of S di of S whole dot di of S plus qi of S is equal to 0. So here we have also, so we know that the contact force, so Ni of S, right? So Ni of, or say N vector, it represents internal contact force. Now, if the rod is inextensible, right? So for inextensible rod, inextensible unshareable rod, N vector is more of a reaction. It's more of a reaction force, is a reaction force. Right? So this is like it won't depend. We won't have any what we say as the constitutive law. Say for example, M vector is a uh, internal contact moment. So what happens is fundamentally we have the three components mi of S, right? Goes from I is equal to 1 to 3. The components of M are the internal contact moment, and then we use something called M1 of S is going to be equal to EI of S, recall the linear bending law. M2 of S is E. So this is EI1, this is EI2, kappa 2 of S. And M3 is equal to GJ kappa 3 of S. And they are what we call materially linear, but geometrically non-linear. And that is the distinguishing factor here. So although they seem to be following the linear bending laws, but if we really go deep into it, we can clearly see that kappa 1, kappa 2, and kappa 3 are nonlinear terms because the structures can go large deformations while still having retaining what you call uh, small strains, right? Okay, so now we come to what we call as the energy functional. So I said for a Kirchhoff rod, the energy function E functional is given in as defined as from 0 to L, the length of this, half of EI1. And mind you that they can even be functions of space. So I can just call it, okay, so one way of writing is just calling them B1 of S, kappa 1 of S whole squared, plus half B2 of S, kappa 2, plus half G, sometimes we could refer to as C of S, kappa 3, where B1 of S is written as EI of S. We are considering a general case where the cross-sectional properties can vary from point to point. We allow the possibility. And for B2 of S, these are just they are the bending stiffnesses. Then we have C of S is equal to just GJ of S. So this is the energy functional for a Kirchhoff rod. But it also has certain constraints. So the constraints are that we do not allow for, as we know that we do not allow for inextensibility. I mean, we do not allow it to be extensible. So in that case, what we do is um, so there are some constraints as well. I'll just call it EL. EL means elastic energy functional. So constraints are that, first of all, R prime of S, uh, the norm of this is equal to 1. And this can also be written as R prime of S dot D3 of S is equal to 1. So this is a constraint that we are putting, and this is the inextensibility constraint. And we also want that this first of all, the second one is we also want that R prime of S does not have any component along D1 of S. So this is 0. So these are like non-shareable. shear impulse. And we'll have two of them. One is for along D1 and one is for. So these are the next shearability constraints, right? And so when we construct a total energy function, then what we call as the augmented Lagrange will be augmented energy functional. And here is where we would like to have this. So E elastic. So E, the total E will be defined as E elastic plus half of like E elastic plus. So this is all, these are all pointwise. These are all in optimization terms. They are called as pointwise constraints. Since they have to be satisfied at every point, so they are pointwise constraints. So when we are what you call imposing these constraints, then even the Lagrange multipliers are themselves functions, right? So they themselves are pointwise. When the Lagrange multiplier will be function, so to speak, right? So in this case, so let's first enforce the uncertainty constraints. Now we can call it N1 S and then R prime of S dot D1 of S. And the second one is N2 of S R prime of S dot D2 of S. And the third constraint is, since the constraints always has to be put in the form of G is equal to 0. So this will be written as R prime of S dot D3 of S R prime of S D3 of S minus 1 ds. Now, when we take its first variations, which of course we are not in the condition to do now because of the constraints that we have on time. So, of course, I will be following it up in separate lectures. So when we take the first variation, and of course, we also have to add some mechanical uh, impose, or maybe so this was just for elastic energy plus the constraints. We can add more energy. So it's like add the external loading energies, external loading, external loads. So what will happen is we'll have say 0, 1 of uh, so typically when we add all this, so we add in terms of so these are loading scenarios, right? So we'll add in terms of delta W. This entire thing we can call is as E constraint, E cons. So here will be delta W will be equal to P of S dot delta R of S ds. So it's like we are integrating force into displacement, right? We can see from here force into displacement plus Q of S. So this is moment, so we require some strain like energy. It will be delta kappa of S d of S. Now what we can do is take variations. Here it will be incorporate. Take variations of augmented energy functional. Take variation of epsilon. Then we have delta is equal to these are all variations. EL plus E cons. Now what we do is then we have something called as a total variation. Maybe variation of total energy. Uh, so we have this variation in total of total energy functional. So the way we first of all we construct the total energy functional. This would be equal to epsilon total is equal to epsilon E, I mean EL E cons minus W, where W is called as the work potential. So I should incorporate the total variation is cons minus delta W. And when we equate delta E total is equal to 0, then and use fundamental lemma of then we use fundamental lemma of calculus of variations. Then what we have is then we obtain force. So all that balance of force and balance of moment equations. Of course, we have skipped quite a bit here, but yeah, we'll follow it up with a future lecture and fully derive all these quantities. Okay, so the next part of our today's study is the ribbon theories, right? Okay, so first of all, a bit of history. So one of the one of the earliest work on ribbons was done by Sadowsky. He had constructed a model. Sadowsky developed a central line based model to study deformation of Mobius bands. So the model was for infinitesimally, I mean for very narrow ribbons. I believe the first thing I should have started with is talk about ribbons first of all. What do ribbons imply? So like as curvature was, I mean the rod was essentially it very much is a one-dimensional object from the perspective of when we look at the longest dimension in the structure. So in ribbons, what happens? They are a structure which are so we have a rod which lie on one end of this extreme. It is a 1D structure. There is a rod, and on the other hand, we have the plate-like structures, plates or shell-like structures. So we have some length L, some width, say W, or maybe A, and some thickness, some very small thickness, right? So this is typically called as L, oh sorry, T. Then rods, these are plate shells. Rods lie somewhere in between. I mean, the ribbons lie somewhere in between. So it will typically be some sort of a structure like this. With some small thickness again. Okay, it will have some thickness T. Length as usual L. The width has A. And for rod, it is like the length is L. And you have some characteristic dimension A to represent the width or the characteristic diameter of the cross section. Right? Okay, so as per dimension, I mean, from the dimensional considerations, we have L, which is much larger than A, or likewise, we can call it A is much larger, much more than A. And here we have A is much smaller than, sorry, T is much smaller than A, and it's much smaller than L. And in here we have T is much more than A, and A is which is comparable to L. Right? So we see that in ribbons we have very wide separation between the characteristic length scales, which right. So this is what makes the study of ribbons very peculiar. In that you have to bridge the ideas from both the bridge between rods and plates, right? And so coming back to the attempts which have been made to understand, to say investigate the sort of the deformation in ribbons. So once I attempt was one of the pioneering efforts uh, was made by Sadowsky. Then Wunderlich followed it up. So Wunderlich I mean, not essentially extended, but he developed these ideas from a different approach. He used the plate theory to come up to, so developed or maybe constructed a model. It essentially derived from ribbons of large width, ribbons of maybe finite width. Differ. Yeah. And then later on in 2015, Orderly and Dias, say, formulated a model which essentially aimed at, I believe it is Orderly and Newkirch. But although Orderly and Dias had developed a model for non-rectangular ribbons, a non-rectangular flat ribbons, right? And it aimed at bridging the Sadowsky and Wunderlich. So this was how it was done. Okay, so now what we do is we let us begin with, we have this ribbons. Sometime back we had studied about rods. So I never mentioned that we're looking at lecture 7 for the inconvenience. So supposed to be lecture 7. Yeah. Okay, so now let's look at the kinematics of ribbons. Now, ribbons are also characterized as 2D surfaces, characterized as surface. So before that, let me is typically done is we consider ribbons as a developable surface in the sense that whenever you bend it, so there are certain lines on the surface which remains lines even during the deformation. So it means that you recall that the curvature of a line, right? So in a sense that we ribbon is modeled by both has been modeled, I should say, not typically, but has been modeled as a ruled surface, ruled, developable, ruled developable surface. Right? So let's look at a kinematics of ribbons here. So it will be some sort of a, say, we consider as a flat, rectangular flat body. We have some center line, which is akin to a rod. We have some center line. Sorry again for the. Then we have this axis, say E, this will be E2. This is E1. Rather, this is E1, this is E2, and this is E3. And this gets mapped to some deformed shape. So to make it more prominent, so some deformed shape. So we have a similar. So we have this D3, D1, and D2. Because of course we'll be mapping it to some local coordinate frame, right? What happens here is at every point, at every point, you have something called as a generators. And this makes beta. It's going to be like that. Let's make it parallel to E1 axis. Is the angle gamma. So E1 axis, and this we typically call as Q vector of S. It's the Q vector of S. And we have S coordinate. Fine. So now let's parameterize it. So, and then we are assuming that's of thickness T, right? That is inherent. So we are lumping everything to a surface, the entire body to a surface. So which means that this is what we are presenting is a mid surface of a ribbon. Fine. So now the way we are going to parameterize it is in reference configuration. So in reference configuration, we have the represented as x naught vector of what we call as the S comma V, and this is given by S E3 plus V E1 plus eta of S E3, where S is an element of 0 to L, V is an element of minus A by 2 to A by 2, and eta of S is nothing but tan of gamma of S, and gamma of S is the angle between the generator and E1 of S. So essentially, eta of S imposes developability constraint. That is the whole purpose of eta of S. In the deformed configuration, what we have is we have x vector of S comma V. This is given by r vector of S plus V, and then you know that E1 gets mapped to D1 of S plus eta of S is there as it is. We have D3 of S because E3 gets mapped to D3 of S. And also the normal to the surface is n vector of S is given as D2 of S. This already implies that n vector, the norm of n vector of S is just 1. It's a unit norm. So this also is, we may recall from our surface, study from that surface theory of surface, is that this represents a ruled surface. It's just that in this scenario, we are considering ribbon to be a ruled. This is and this is going to be our generators. This is gamma of this. Right? So it says that ruled surfaces, not all, some of the ruled surfaces are developable, but not all, right? It's not all developable, but what it seems that all developable surfaces are ruled surfaces, but not vice versa. As an example, even a hyperboloid is modeled or can be modeled as a ruled surface, but it has a non-zero Gaussian curvature. Right? Okay, so far so good. Now let's go on to determining some quantities such as covariant basis vectors. So I have started using all those terms which we will discuss later in future videos or future lectures, right? Covariant basis vectors. Now let's determine it. So how are covariant basis vectors? So it's like basis vectors which are determined just by differentiating the mapping with respect to the uh, contravariant uh, arguments or the parameters. So here we are the coordinates, right? So we have x, and this gives out to be r prime of s. I'll just put it up here so that you see what's going on here. Plus v d1 prime of s plus eta prime of s plus eta of s, right? Now we are using all those ideas about inextensibility and all. So this causes r prime of s will be d3 prime of s plus v minus kappa 2 of s d3 of s 3 of s d2 of s and plus v eta prime d3 of s plus v eta of s minus kappa 1 of s d2 of s plus and we'll do some rearranging. Then we can write this as v eta of s kappa 2 of s d1 of s plus v kappa 3 of s minus eta of s kappa 1 of s s Okay. And then we have plus 1 plus v eta prime of s. Fine. Now is the term for g2 is equal to parse. And then this is given as g1 of s eta now the next step is that is, and it so happens that g1 and g2 also span the tangent plane at s on the central line. Right? So you know that g1 and g2 span the tangent on the central line, span the tangent plane of the set, and so which means that g1 cross g2 should result in, so will result in normal to the surface. The ribbon surface at S, or maybe normal to the tangent plane. So I should call it TS capital, maybe capital P for, or maybe capital R for ribbon. So TS capital R. So now G1 across G2 gives us the, I'll write the final expression is equal to minus V kappa 3 of S minus eta of S D3 plus plus v eta prime of s minus v minus and since they have it has to be, since g1 cross g2 is the normal, right? It's is equal to some lambda vector normal, which is equal to lambda of d2 vector. This implies that so right, so this implies that g1 cross g2 dot product with d1 of s has to be 0. So this means that v kappa 3 of s minus eta of s equal to 0. So it's a kappa is for all v. Likewise, taking dot product with d3 of s implies that it's also v eta of s. So it is v for all v. So therefore, the condition of therefore g1 vector is, now I can just bring it up here. So we'll have just these two terms. Enough. The coefficients of first fundamental is as f is equal to g1 dot g2. Right? And let's look at the second fundamental form. Is L is equal to x axis dot n, which is the same as minus g1 dot n and n1, which is like I should just call it parcel n by parcel s, and this is going to be equal to minus v eta of s upper 2 of s 3 of s 1 of s. M is equal to x sv g1 dot parcel n by parcel v, and this is going to be 0. N is equal to x vv dot vector is equal to minus g2 dot parcel n by parcel v, also going to be 0. Fine. So now what we do is let's put in matrix form. The first R and what it says, recall that we had learned in the curvature lecture on curvatures that the representation of the shape operator or the Weingarten map is minus of grad n in the director frame this is not in director frame, this is in the covariant basis frame, right? Which is J1, J2, and N. Gives us the curvature matrix kappa, and I'll call it in script kappa. So minus this in its representation in J1, J2, and this is going to be equal to F1 inverse right? Okay. So now our idea, now the goal is to determine the kappa matrix. This gives us which is a 2 by 2 matrix, as is evident from the form. So it is a 2 by 2 matrix. So F1 is like E, F, F, G, inverse of L, M, M, and is going to be equal to 1 by EG minus F squared, G, E minus F. That's and as we recall here, the expressions are just all of them are zeros, so we'll keep it as it is. And finally, we have 1 by EG minus F squared. Okay. And then we can write this as LG 0 and then minus LF 0, right? Okay, so we know the two facts here. The mean, the Gaussian, now let's determine the Gaussian curvature, right? So the Gaussian curvature capital K is equal to the determinant of kappa matrix, which is equal to 0, right? Because you clearly see that LG into 0 minus or plus LF into 0 is 0, right? And then we have the mean curvature, S is equal to half of the trace, and this is going to be equal to LG plus 0, which is LG, divided by 2 into EG minus F squared. Let's simplify this further. So H is equal to LG minus 2EG F squared. So the expression for L is given as this long expression here. But before that, because since let's take a slight digression here, that the geodesic curvature of a curve lying or of a curve on a surface remains invariant under isometric deformation. So we are considered that the ribbon surface is developable, and also that the center line is inextensible. So it means the length of any curve lying on the surface do not change under deformation. So essentially we are looking at as isometric deformation. So because always the geodesic curvature of a curve on a surface is constant, right? So for the center line, kappa g is called as the geodesic curvature. So it will be like, so geodesic curvature is kappa g. Kappa g is equal to kappa g of S is equal to R double prime S dot d1 of S. This is how the definition goes as this is d prime of S dot d1 of S, d3 prime of S, and this comes out to be kappa 2. And this is like in deformed configuration, right? In deformed configuration. And in reference configuration, kappa g of S is equal to the same definition. So it will be what we happen is this becomes to be S E3 double prime dot, and D1 is the same as E1. So this gives us the first derivative of S E3 is just E3. And then we take its derivative again with respect to S. And we recall that E3 is a constant vector, so it's 0. So which means that Kg of S is 0. And this is also equal to K2 of S. So sorry, kappa 2 of S is always 0. This is a very important. This is what we call as the geodesic constraint. So what happens is now let's just let's put what is L, E, F, G, and L. Now E is equal to E is equal to so kappa 2 terms will go away, so we'll have just this term. So 1 plus nu prime just this part. Quite simplified. Now F again will have sorry, it's just this also goes away. We're left with here, and this term also goes away. So we're left with this. And the last and the Z term is as it is. There is no change. Let me put it up here. And last term, what we are looking at is L. So L comes out to be this entire thing. Bring them here. This first term goes away. And here again, this nu 2 is not there. And then kappa 2 is identically 0. So you have n of S. This is L. Now let's simplify it. So L is like kappa 1 S 1 plus V eta prime of S into 1 plus eta square of S divided by 2 into 1 plus V of S tau of S, then into G 1 plus eta square of S minus F squared, and F is 1 plus V eta prime of S whole square eta square of S. Now simplify it a bit. And we have kappa 1 of S 1 plus eta square of S. And since we have V eta prime 1 plus V eta prime on the numerator denominator, so we just this comes out to be 2 into 1 plus eta square of S This was supposed to be 0, which is squared. Yeah. Sorry, I made a mistake. Yeah, it's 0, I think. Yes. So this is 1 plus v eta prime of s. Then we have 1 plus eta square of s minus eta square of s. And then we have finally just kappa 1 of s, 1 plus eta squared of s divided by 2, 1 plus v eta prime of s. Done, right? So now let's use the energy formula, the elastic energy of a plate. So I'll call it energy functional. Plate made up of a homogeneous isotropic Hookean solid is epsilon E is equal to d by 2, and d is the flexural rigidity, nu trace of kappa whole squared plus 1 minus nu trace of kappa squared ds. Where d is equal to et cubed by 12y minus nu squared, and nu is the Poisson's ratio. Poisson's, so I should call it nu. Fine. And this, we have one identity which can be easily shown, is that trace of kappa whole square is equal to trace of kappa squared plus 2 determinant of kappa. And we know that the Gaussian curvature k is equal to determinant of kappa, which is 0 here. And the trace of kappa is the mean curvature half of trace of kappa. So this implies that trace of kappa is equal to 2h. So fine, so far so good. Now we have E is equal to d by 2. Makes the substitutions. So we have nu into 2h whole square plus 1 plus nu. This also 2h whole square. Now let's still keep at as ds, okay? And this ds is integration over parametric space. I mean, as of now, it is over 3D space. Over 3D space. And we are doing a surface integral, right? So this is a surface integral. This entire thing is a surface integral. So then we'll make some You know that one nu and then 1 plus 1 minus nu, it's just like, so it's like just 2h squared. And now we have that ds is also given as dx dy, and this will be equal to, using Jacobian j, then we can write in terms of ds dv. And j is nothing but determinant of, the norm of g1 cross g2, which happens to 1 plus v eta prime of s. And then we have, so this is what j is. So we can write this as 1 plus prime of s ds dv. And now the end limit. So s is equal to 0 to s is equal to l, and v is equal to minus a by 2 to v is equal to a by 2. This comes out to be d by 2 s equal to 0 to l, v is equal to minus a by 2 to a by 2, and then 2h is given as, right? So we had, this implies that h is equal to this thing here. We can just copy this, right? So this is like, so 2h is, this does not exist anymore. This squared 1 plus v eta prime of s ds dv, and then we can write it down in terms of s equal to 0 to l upon 1 squared 1 plus eta square of s, and then integral of minus a by 2 to a by 2 for v, and then dv by 1 plus v eta prime of s into ds squared as well. And finally, this term evaluates to 1 by eta prime log of a by 2 by 1 minus eta prime. So finally, we have d by 2 0 to l upon square of s, and we can multiply a here. It will become 1 by a eta prime log of 1 plus eta prime of s a by 2. And this term we can also call it as g of s eta and eta prime. And this is what we call as the celebrated Wunderlich model. Is the Wunderlich ribbon and in the limit for a narrow ribbon, eta prime tends to 0, which implies that the limit of eta prime tending to 0 is 1 by a prime eta prime log of 1 plus a eta prime by 2, 1 minus a eta prime by 2. This goes to be 1. And then we cover what is called as the Sadowsky model. So we have E Sadowsky. And this is given as 0 to 1 kappa 1 square of s This is the Sadowsky model. Sadowsky. Okay, so although we have come to an end of this lecture series on ISSS course, but I'll be continuing the lecture series, although not in an ISSS format, but it will be through. I'll be continuing this lecture series, and what remains to be covered remains for other topics to be topics. I don't know what to say, but it's like remaining to be covered is, first of all, curvilinear coordinates, the curvilinear, rather tensor calculus. One such theme where we will look at curvilinear coordinates, the or determine gradient, divergence, and cross product or vector product. And also look at calculus on such surfaces. Then we look at covariant, contravariant basis functions. Covariant, then we look at Christoffel symbols. This for the tensor calculus part. Once we have mastered enough tensor calculus, then we would move on to studying shell theory. So these are the topics which remains to be covered, and I'll be soon covering them in the same playlist. So please be uh, on the lookout for the future topics, future lectures on the same playlist, right? So with this, I'm closing today's session as part of ISSS PMR of lecture sessions. For any doubts, please mail me at Krishna A G R A C on linked. So this is my email, and on LinkedIn, I am at just search me on KC Avatar. So yeah, thanks for the patience and for following on the lectures. Yeah, with this I'll close the session. Thanks.